Hey, I'm Todd Mostak, founder and CEO of MapD. MapD, we're a startup based in San Francisco. We build a GPU-powered database and visual analytics platform. So we literally use GPUs. So you think about GPUs, they're video cards originally designed to accelerate rendering graphics to a screen. We actually use them for something very different, primarily a very fast SQL database that can leverage the parallelism of GPUs. To render, it was originally designed to render graphics to a screen. We can use it for database, but we also use it for visualization. So it's a full stack, vertically integrated visual analytics and database platform. And I'll tell you a little bit about the platform in general, and then some of the tricks that we do to do visualization at scale. Think multi-billion row data sets with response times in milliseconds. So everyone's probably seen slides like this. Basically, we're drowned in this deluge of data. Data's getting 50% bigger year over year. People don't know how to handle it. The normal approach is to scale out. It's to sample. It's to pre-aggregate. But all of those approaches fail at different times. And often you need sub-second response on streaming data that can't be pre-aggregated or sampled. And so what do you do there? So if you look at CPUs, CPUs just aren't keeping pace. So ever since 2002, basically chip designers hit a clock speed wall, and they hit like 4 gigahertz and basically realized they couldn't turn up the clock speed without an exponential increase in heat production and energy consumption. And so after that, they said, okay, Moore's law is still continuing. What are we going to do with all these extra transistors that Moore's law gifts us with every year? And some of that went into making chips smarter, making them more optimized, adding more cache. Some of it went into adding extra cores, so starting to become parallel. But today we still live in a world that a lot of programs can't exploit the parallelism of CPUs, of multi-core CPUs. And then if you're an analytics platform and you're already writing optimized code, you may not get the full advantage of all the transistors that, say, Intel is adding to its chips every year, which are primarily designed to make dumb code run faster. So this is where GPUs come in. So a GPU, again, is a graphics processor evolved to be parallel. People realize that rendering video games is a parallel problem, that you can basically treat each pixel separately and render basically polygons to the screen in parallel. At some point, people realized, hey, we can do a lot more with this than just render graphics. People started bolting on all sorts of things into the graphics pipeline. 10 years ago, NVIDIA had the foresight to basically design a general purpose programming language called CUDA, which was followed by maybe a more open programming language called OpenCL, and basically allow people to do generic programming for GPUs. And so GPUs took off for HPC, and then more recently for machine learning. You've probably heard about them in the context of deep learning or neural networks. And then finally for data analytics and database operations. And so that's where we come in. And we're very lucky to have GPUs which are very simple at their core. They're basically very kind of dumb cores, but there's tons of them. So think of them thousands per chip, thousands per card. And so we can leverage this, and year over year, even without our software getting faster, they add more of these cores, and GPUs might get double their speed every 2 years. And it's not just the teraflops or the compute bandwidth, but for data analytics, often it's memory bandwidth. So we can actually leverage not only the massive compute power of these GPUs, but their fast memory, which is often measured in near terabyte per second per card. So we can have 5 or 6 terabytes a second of scan bandwidth per card. And that's very important if you're doing analytics, because a lot of these things are I/O bound. And by being able to scan data that fast, we can actually crunch literally many billions of rows in 10, 20 milliseconds. So that's where MapD comes in. So MapD was built from the ground up to leverage the parallelism and the graphics power of these GPUs, so both of them. And so it's a two-part equation. So at its core, it's this analytics SQL database that is orders of magnitude faster than CPU solutions. So literally, it'll be 100 times faster than something like Redshift, Vertica, MSQL, or the like. And then because this use case is so often visual exploration at scale, taking billions of points and being able to slice and dice it in real time, we built a visual analytics layer called MapD Immerse, which ultimately is a web-based JavaScript kind of cross-filtered exploratory engine, which I'll demo for you in a minute. But it's key. One of the key differentiators is it can not only leverage the speed of our backend, but can also leverage the ability of us to use the GPUs to actually render graphics. So if you look at this map here, and I'll give a demo, this is actually rendered right on the GPUs on the back end and passed to the front end as a compressed PNG. So typically, we're not your data store reference. Our clients, whether it's Facebook or Verizon, we have hedge funds, kind of across the spectrum. They typically use us on top of another store reference. So you think you might have Hadoop as your data lake, you might have Teradata or MySQL or SQL Server as kind of your data warehouse. We sit on top of that, we can pull data in, we can act as like a hot cache on top of that via JDBC. Or alternatively, we can bring in streaming data through Kafka. We're very fast at that. And then you can actually use, MapD, you can use it to power something like Tableau or other non-visual output, or you can use it with Immerse, which is the visual analytics platform I was just speaking about. So I'm just going to speak briefly about a few of the things we do to tune it for performance, and then I'm going to turn to the graphics API and focus most of the talk on that, just because I think it's more relevant here. But you can't have fast visualization without a fast analytics or database platform underneath. So MapD was built for speed. If we were just blindly using these GPUs without regard to where we put the data or where we did the computation, we wouldn't be seeing the speed ups that we do. So the first thing we do is we typically use multiple GPUs per server, often up 8 or 16 GPUs per server. And you can go to Dell HP or Supermicro. You can go to the Amazon Cloud. Google Cloud just launched GPUs yesterday. Azure has them. IBM has them. So basically, they're everywhere. And you can get a server with up to 16 GPUs. And what we actually do is we cache the hot data across the memory of those GPUs. So think of that as our L1 cache. The memory bandwidth of the combined GPUs is usually 5+ terabytes a second. So if the data can fit there in the hundreds of gigabytes of GPU RAM, and of course we're compressing the data as a column store, we'll basically be able to push through billions of rows in milliseconds. If it doesn't fit there, we spill into CPU RAM. If it doesn't fit there, we spill into SSD. And we can actually execute on GPU or CPU at the same time. Another thing that we do is, again, we're very focused on speed. So a typical interpretation engine for a database wouldn't cut it. So most databases actually interpret their queries, just like Python, basically interprets the runtime code. So we actually compile our queries on the fly, and we use something called LLVM, which is an Apple-backed compiler infrastructure to basically build our queries, build custom functions for our queries. And the great thing about LLVM is that we can target different architectures. We can target CPU, we can target GPU, and we can actually run on both simultaneously. So getting to the key, I guess the key focus of the talk here. So if you have a typical BI system, you usually have a backend, something like Vertica, maybe something like MemSQL, maybe something like Impala or Teradata, and then you might have a front end, whether it's an app like Tableau or it's a front end like Looker or web front end like Looker. And those systems tend to work pretty well if the data set sizes are manageable, and then particularly if you are not rendering very granular result sets. So if you're going to group by US state and there's only 50 states, it's not a problem because you can run that query on the back end and you can send the 50 results from the back end to the front end. It's not going to overload your network connection. But if you actually have a huge result set, say you're rendering every tweet, geo-coded tweet, or every political donation, every call record, you might have millions, hundreds of millions, or billions of points, or you might have millions of census blocks that you want to render as polygons, then it's going to be very problematic to try to get that from your back-end server to your front-end client. In fact, you could have tens of gigabytes or hundreds of gigabytes of result data, and it might overwhelm your connection. And even if it did get to the front end, you're going to have trouble rendering that in real time because the front end is often a thin client. It can't actually, doesn't have the graphics prowess to actually render that in real time. So MapD takes a different approach. MapD actually has all these GPUs on the back end. So we're running, even if they don't have video outs, they're server grade GPUs built for compute. They still have the graphics pipeline. They still have OpenGL pipeline. So we can actually use that. We can run the SQL query right on the GPUs, and we can take the result set, and without copying it to even CPU memory, we can actually feed it from the CUDA pipeline, the compute pipeline, to the rendering pipeline, the OpenGL pipeline, and basically render it, and then we can composite the renderings between the multiple GPUs and create a compressed PNG, which might be 100 kilobytes instead of the tens or hundreds of gigabytes of the raw data, and we send that to the front end. And we've built our front end where that feels fully interactive, where you can actually mouse over the data, inspect it, get metadata about it, even though that the user has probably no idea they're interacting with a static PNG. And some of the key use cases for this, of course, you can use it for things like scatter plots, but we find a lot of use cases for geo-visualization. So needing to render point maps or heat maps or polygon choropleth maps at scale at a granular level of detail. So a little bit more detail about the actual pipeline. So you normally would have your web front end, which is Immerse here, although you can build custom apps on top of MapD's backend with our API. We use something called Vega. So Vega is actually a open source spec out of the University of Washington, the same lab, Jeffrey Heer's lab, who did D3. He's actually an advisor to the company. So we use Vega to basically define the data to visual specification. So you could imagine you have, let me just skip ahead a few slides. You can imagine that you have this map, and this is every political donation in America, for example, and you want to say longitude is X, latitude is Y. The color is going to correspond to the political party. Red is Republican, blue is Democrat, of course, and the size will correspond to the size of the donation. So Vega is a very nice specification where you can map the data attributes to the visual attributes. So we use this to actually drive our back-end visualization, where we can put a query in, and then we take the output of that query and use different scales, kind of like you would in D3, to actually drive the visualization. So we use that, and it's used to describe the back-end visualizations. And then once it gets to the server, we actually not only run the SQL query, but we compile the SQL query, but we also compile the visualization shader. So shader is a graphics program that runs on the GPU, and anytime we see kind of a new template, we'll actually compile it on the fly and then build a custom shader to render the user's visualization. We also do some clever stuff because, again, you want this to feel interactive. You don't want to make it feel static. So if a user hovers on a point, say on this tweet map, you want it to pop up and show them the actual tweet under the mouse. Even though that we're very fast, we could do this in SQL in probably 20 milliseconds on a 3 billion row data set. It's still too slow if you have a lot of users actually mousing over points. So we did something where we actually built a hit testing pipeline where, in addition to actually rendering the image, we'll actually render the row ID into a graphics buffer, the row that landed on top of each pixel. And that way we can do a simple constant time lookup. Whenever a user mouses over a pixel, we can get the row ID and then basically actually get the raw data for that and return it to the client. And I already went through this. I want to make sure I leave time for a demo. Here's just, basically the CUDA. CUDA already has interoperability with OpenGL. So CUDA, again, is the compute pipeline. OpenGL is the graphics pipeline. The great thing is that you can actually transfer data between the two without copying, which further enhances performance. Each GPU renders its own results, copies the render buffers to a primary GPU for compositing, and we can actually do a 3 megapixel render on 8 GPUs in 25 milliseconds. So you can literally push almost 30 frames a second for a user, although we typically don't, but you can. So just in brief, what is MapD about? Our core beliefs are we believe that we're at an inflection point in compute, that CPUs just don't have enough gas, literally, to power the data revolution, that you need more horsepower, you need more compute power, you need more rendering power, and that's where GPUs come in. If you're using GPUs, which we believe are the fastest hardware for this kind of use case, you also need the fastest software. So MapD was built to be optimized to run queries and build visualizations at real time, even over massive data sets. Speed at scale, our sweet spot is not, data sets that are under 10 million rows. We can obviously do that, that's great, but our clients tend to use us for, 10 million to 10 billion rows. We're adding a distributed framework, so we have clients wanting 100 billion rows interactively, web-click data, geodata, so that's what we're optimized for. And that we believe integrated analytics is key here, that you want to control the whole stack so that you can deliver not only the fastest queries, but the fastest biz. And looking to the future, we're interested in seeing what we can use these GPUs for to actually accelerate kind of data analytics or data science operations like machine learning. It could be a subject for a future talk. Cool. So I believe I have about 10 minutes. So I'm going to cut to a quick demo. Let's see here. I'll start with this. So this is actually an interesting data set. This is 1.2 billion rows. This is every taxi ride in New York City from 2009 to 2016. So here you have standard D3 rendered graphs. These are powered by our fast SQL backend. Here's actually an instance of the backend rendering that I was talking about. So this is the 1.2 billion points. There's no way that you'd actually want to render this on the client or pull all that data. So this is actually server rendered. However, if I hover over any of these points, I can actually get metadata about it. And that's because we're doing this ultra-fast hit testing, so the data actually feels like it's in the front end. So just to give you an idea of how interactive the system is, I zoomed in here. You saw all the charts update. We're actually looking at the drop-offs here colored by their pickup borough, so you can see that they're coming primarily from Manhattan and Queens. You can see an uptick in rides over time. We built our front end on the cross-filter framework, so if I just brush this, I can see that the longer rides are going to Manhattan, the shorter rides to Queens. And we can do this so interactively. We're actually querying, all three of these charts are hitting this 1.2 billion row data set, and we're literally running these queries in 20 or 30 milliseconds, which is probably 100 times faster than you would ever get on a CPU database. So that's how it can be so interactive. The great thing about having a system like this is that I can brush here and actually discover insights in real time. So if you were to sit here and have to go get a cup of coffee for your query to return, you probably wouldn't actually find interesting things in your data, or else it would be very laborious. So you can see here, if you actually look at this, this is I believe the Pan Am terminal that was knocked down at the end of 2013. I'm not a local, so you can actually see it disappear on the map. So a lot of our customers find all these insights that they never realized existed in their data simply because they didn't have the power to actually investigate it in real time. So it's very easy to add another chart. We definitely built it not only to be easy to use, but also to be, not only to be fast, but also to be easy to use. So if I wanted to look at a different dimension, I wanted to look at how people are paying for their taxi rides over time, I just do that dimension measure, switch to a row chart, and then I put it in. Now I can cross-filter on it. I hope that was positive. And so I can see cash is going down, credits going up over time. Let's see if I can give you a quick two other demos, and then open it up for questions. This is our streaming Tweetmap, a little bit of a smaller data set. This is running on the equivalent of 1 GPU, but about 200 million rows. Here I'm coloring by the source of the tweet, so you can see France tends to use iOS more. We can cross-filter on anything. I can look at iOS versus Android. I could, for example, see that Turkey tends to use Foursquare, and so does Latvia, I guess. So what's cool about this is it's actually streaming data, so this is something else that MapD is very good at. Because we don't have to index any of the data, we're basically using the brute force of these GPUs. We can actually bring in streaming data very fast in real time. So you can imagine at Facebook and Verizon, we're employed in streaming use cases. It's something that's good because we can actually query data up to the second. So I'm going to zoom in here to the US, and you can actually see the top hashtags over here, which we're computing dynamically. This is not pre-computed. So you can see, I think we just lost our first spike. So we got this rolling window here. We actually dropped data off the end. But if we actually zoom in to this spike, you can guess what it is. It's the World Series. So you can see, what are people saying about the Cubs? I'm sure in Ohio they're saying they suck, but people are pretty happy in Illinois where you can see this clustering. And then if we actually zoom to this one, you can imagine what this one's about, November 8th. So who's excited? So election night, Trump, not my president, and you can actually get very granular here. So we could go into New York, and one of the interesting things is I actually tweeted the other night. So if you turn your geocoding on, I tweeted the other night, and I took this picture. I was walking by Trump Tower. So not many people were out there, but it was Monday night. So very easy to use. You can drill down, you can get very granular. Whereas we could look for think Trump Tower is right here, right? So we could even go down to the grain level. We could say I only want to look at Instagram and, you know, actually look at images here. Okay. Not associated with any of that, so. Cool. Yeah, that gives you an idea of the power of the system. And one last thing that we did, which is already a little bit out of date, this was every political donation in the US from 2001 to 2016. You can basically see here the blue states, the red states. Again, you can get very granular here. This is all public data, by the way. You can see how blue New York is. You can see how much New York donated to, I guess, Hillary. One of the interesting things here is we can add a filter here. I'm going to look for Bernie. And you saw the autocomplete there. One of the nice things is that's fully dynamic. We can just search this text interactively. You can see all these donations to Bernie, and I'm going to actually do a donate amount less than $2. You can see that Bernie got 112,000 $1 donations, which is pretty interesting. But if you actually looked at Hillary only got 4,816. So Bernie had the grassroots support, I guess. Cool. Yeah, that's it for the demos. Happy to take any questions. Cool. Sure.
Hi, that looks amazing. I'm curious about the structure of the data that goes into MapD. Where does it excel at? So, you know, in terms of like joint strategies and structure of the data, distribution of the data, does it favor wide tables or do star schemas? How would I, if I have a big enterprise data warehouse, how would I have to restructure my data to have MapD excel at querying it?
Yeah, that's a great question. Thank you. Yeah, so you know, MapD is SQL under the hood. It's not SQL 99. It's basic SQL 92. We can do multi-way joins, particularly PK/FK joins work well. Star schemas work well in MapD. We're actually adding that into the UI as we speak, so that you could do this dynamically. In general, like if you have two big tables, we generally argue that you should pre-join and flatten or denormalize. I think that's not just us, that's a lot of analytics databases that if you're going for speed. However, we've done some pretty heavy joins doing it on the fly. You have to remember that every one of these charts is actually going to do the join for every query. And it works pretty well. So again, you know, you might see a bit of a performance hit, but it's still going to be interactive because we just have a lot of speed and power to spare. So cool, thank you.
How are you guys compared to Spark in terms of performance?
Yeah, no, it's a great question. So I think just by virtue of being on the GPU versus CPU, and then you know everything's written in C++ and CUDA, and then compiling our queries on the fly, those three things alone mean that we're going to be significantly faster than Spark. I think one of our hedge fund clients benchmarked us against a 20 server Spark cluster and found us to be about 80 to 100x faster on a single node. I know Spark's getting faster, so some of the stuff we did, they're actually moving to, I think, a query compilation engine. So I'm certain they'll get faster as well. I also know that they're starting to look at, there's GPUs on Spark. To my knowledge, it's not used for the SQL. It's more for offloading machine learning operations. But I mean, Spark is an amazing framework. You shouldn't look at us as, we're not gonna have all the features of something like Spark. I mean, hopefully someday we will. It's a leaner, you know, faster machine, I guess, but it won't be everything you would get out of your Spark or your data warehouse. So, oh, cool. Yes? Oh, sorry. Sorry, I think she's got the mic. Sorry.
A quick question. So can you please elaborate on what happened in 2014 to GPUs? In your early slides, you were showing the graphs.
Yeah.
And there was a spike in 2014, so I'm curious as a...
I think it may, So and this is particularly NVIDIA. I think that's probably when they went to their Kepler architecture, which was significantly more advanced. They also, it's the first time I think they may have added, maybe not the first time, but they re-added 2 GPUs per card. So they got a significant boost. This is a measure of what you can get in a server, like, you know, a GPU server with 8 GPUs versus a quad socket CPU server. The GPU, you know, but yeah, I think there was a huge, there was an architectural move there, and there was the dual GPU thing. They also made a huge stride, which I'm not sure is reflected on this, with Pascal, their latest architecture, which you've probably heard about. Again, the great thing about GPUs is as soon as they get a node shrink, not to get too technical, but every time they can shrink the transistors, they basically just throw it at adding more of these cores. So the primary driver of speed is the fact that they're just being able to add more of these cores for the same power envelope. Cool. I think, yes, sir.
I love how you render the extra channel with the row ID so that you can just send a PNG to the front end and people can actually sort of click on the data. But what do you do if there's billions of records? It's very likely there are going to be multiple rows on a single pixel. So what happens in that case?
That's a great question. Yeah, we have 2 modes. One is the fast mode, which just grabs the topmost pixel, which for casual use is often just what people want. And then another where we can actually grab all the dots or all the things that were rendered under that point. And we have to actually use a regular SQL query for that. Thankfully, it's still going to be fast. It's going to be 20, 25 milliseconds over a big data set. But the hit testing is probably sub-millisecond. So you can see that it's still interactive, but if you have a bunch of users, it's going to incur a heavier cost. So you have to, like, you can choose. In our front end right now, it's just top pixel. But we have clients who actually need to get all the data under the cursor. So, all right, I'm done. Thank you.